Have you ever watched an AI agent, one you're actively paying for by the second, just get completely stuck in an endless loop?
Oh yeah, it is painfully common with these systems.
Right. You give it a multi-step prompt, maybe asking it to navigate a complex website or use a software tool, and at first it seems totally fine.
Like it knows exactly what it's doing.
Exactly. But then it starts, clicking the wrong button, or it just keeps feeding the exact same useless command into a terminal over and over again.
Yes, and you can see the failure happening in real time.
But the system itself just competently marches forward, right? Completely oblivious to its own mistakes. And it is frustrating, but more importantly, it wastes a massive amount of expensive computing power.
It really does. It is a ubiquitous problem right now in the whole landscape of autonomous agents.
Welcome to today's deep dive. We are jumping into a really fascinating piece of state-of-the-art Gen AI research today titled Doomed from the Start.
It is such a great paper.
The mission today is to unpack how researchers have figured out a way to, well, essentially read an AI's mind, to predict if it's going to fail a task long before it actually makes a mistake.
Because if you can do that, you solve the core problem we were just talking about. Modern LLM agents tackle these multi-step tasks that consume thousands of tokens.
And waiting for a formal timeout or a wrong answer just means throwing money away.
Precisely. If we could detect those doomed episodes early, we could just reallocate that compute. Maybe use it for retries or just save on serving costs.
So to solve this problem of wasted compute, we first have to ask, how do we actually know an AI is failing? Like, why can't we just look at what it's typing?
Well, that is the intuitive approach, right?
Yeah.
Monitoring what the researchers call the surface behavior.
Meaning the actual text output.
Right. You build a scoring mechanism that reads the text. It looks for error keywords, or maybe it notices the agent repeating an invalid action.
That makes sense to me. I mean, if the environment spits back an error message, that should be our cue to hit the kill switch, right?
You would think so. But the data shows that reading surface behavior takes way too long.
Really? How long are we talking?
They analyzed datasets where agents were doing multi-step crafting recipes, specifically in an environment called TextCraft, and they found that a surface score is barely better than a coin flip during the first round.
So it is just guessing at that point.
Basically, yeah. The behavioral evidence needs time to accumulate. The data shows surface scores only become really informative around round 3 or round 4.
But wait, by round 3 or 4, hasn't the window to save compute mostly closed?
That is exactly the issue. Over a third of episodes have already naturally finished by then.
Yeah.
The useful compute is already gone.
Okay, so the researchers realized that relying on the text output is inherently too slow.
Right.
So they decided to look inside the AI instead.
Yes, this was their big aha discovery. By placing lightweight probes on the agent's internal representations, they found the AI actually knows it is failing much earlier.
Okay, let's unpack this. They looked specifically at the residual stream hidden states at the final token of a generated action. What does that actually mean?
So think of the residual stream as, well, the central nervous system of a transformer model.
Okay.
When you feed a prompt in, the model doesn't just instantly output a word. That input travels sequentially through dozens of layers.
So it's building the response step by step.
Exactly. At each layer, it reads information, processes it, and writes new context back into the stream. It is this evolving mathematical vector holding the thought of the model before it becomes text.
So it's like a factory assembly line. By layer 14, the product, which is the AI's thought, is half built.
I like that analogy, yeah.
We don't have to wait for the car to drive off the lot and break down on the highway to know it's flawed. A quality assurance inspector can just look at the chassis on the assembly line and see that the frame is fundamentally bent.
That is exactly what is happening. The internal activations already possess the mathematical signature of failure, long before the final layers translate that into confident-sounding text.
And you mentioned they tested this on specific models.
Right. They used 2 state-of-the-art models in the TextCraft environment. For Quinn 2.57b, they peaked at layer 20.
And the other one?
For Llama 3.23b, they looked at layer 14. They just extracted a small vector from the model's own ongoing calculations.
And this internal signal completely beats the surface-level approach, doesn't it?
Oh, totally. The internal probe's accuracy at round 1 already matches or beats the absolute peak accuracy that the surface scorer eventually reaches much later.
Wow. And the internal signal actually peaks at round 2.
Right. So it provides a strong signal exactly when you need it, early on when you can still save the most compute.
Let me get this straight. We've been waiting for these models to stumble around and fail in plain text over multiple rounds when the internal math knew it was doomed in the first 2 seconds.
Pretty much. The AI internal state gives away its failure early.
But knowing an AI is going to fail and safely pulling the plug are two different things, right?
Oh, absolutely.
Because if we intervene too aggressively based on this internal signal, we might kill a run that was actually about to figure the task out.
And that is the biggest challenge. You don't want to accidentally kill a successful run. That silently destroys your task reward.
So how do we pull the plug safely?
The researchers introduced this concept of global success recall. It is basically a mathematical guarantee regarding the harm you might cause.
Global success recall. So meaning we guarantee we preserve a specific percentage of episodes that would have succeeded.
Right. Say you target a 90% or 95% global recall. You are setting a strict floor.
You're saying I'm okay with accidentally killing 5% of my successful runs to save massive compute, but you absolutely cannot kill more than that?
Exactly. But the problem is that risk accumulates across multiple steps.
Because the episode unfolds over multiple rounds. Round 1, round 2, and so on.
Right. If you check the AI at every single round, the chance of a false alarm grows. Per round guarantees don't magically stack into a safe episode-level guarantee.
So if checking multiple times is mathematically risky, why not just put one massive bouncer at the door?
What do you mean?
Like, why not just check once at the most optimal round, maybe round 2 where the signal peaks, and just be done with it?
They actually tested that single gate baseline. The flaw is that episodes terminate at different times.
Oh, I see.
Yeah, different prompts revealed they are doomed at different stages. If you only check at round 2, you completely miss the easy-to-spot failures from round 1.
And if you check at round 1, you miss the subtler failures that only show up in the residual stream by round 3.
Exactly. You leave money on the table either way. A single gate fails to capture all the savings.
So what is their solution?
They built what they call the recall-controlled probe cascade.
The Cascade. How does that work?
It places a gate at each of the first 6 rounds. But to manage that compounding risk, they use a strict statistical method called Klopper-Pearson calibration.
Okay, Klopper-Pearson calibration sounds intense. How does it actually manage the risk?
It calculates a worst-case scenario given limited data. It ensures that even with noisy validation data, the probability of accidentally aborting a good run is rigorously bounded.
So instead of spending all their risk budget at once, the system searches for the best way to distribute that budget across multiple rounds.
Yes. It maximizes savings while strictly honoring that global recall floor we talked about.
It dynamically distributes the risk to where it buys the most compute savings. That is brilliant.
It really is an elegant mechanism.
So we have the theory, but does this actually translate to real-world compute savings? I mean, the numbers in this paper are just wild.
They are very impressive. What do you think of the results?
Well, at a 90% global recall target, this cascade saves a massive 47.1% of inference compute for Quinn.
Almost half the compute cost just erased.
And for Llama, it's 37.2%. That is huge for anyone running agents at scale.
And circling back to your single bouncer idea, the data proves that distributing the budget across the cascade saves 1.6 to 1.7 times more compute than the best single gate policy.
Wow, so multiple calibrated gates really is the key.
Yeah, and interestingly, a uniform policy, where you apply the exact same strictness at every gate, saves almost nothing.
Because it spends too much risk budget on late rounds where very few episodes are still running.
Exactly.
Now, there is an ablation study in the paper that really surprised me. What happens if you combine the two methods?
Oh, stacking the behavioral evidence on top of the internal probe.
Yeah. Intuitively, more data should mean better predictions, right? What if we look at the text output and the hidden states together?
What is fascinating here is that it adds absolutely nothing.
Wait, really? Nothing at all?
Nothing. Stacking surface features onto the internal probe yields no extra savings. The cascade performance stays flat.
So the hidden states already perfectly capture everything the observable behavior eventually reveals.
Yes. Whatever the model is going to type, the residual stream has already locked it in mathematically.
The text output is just a lagging indicator.
Precisely. To go back to your assembly line, once the inspector sees the chassis is broken at layer 14, watching the car drive off the lot doesn't give you any new information.
The flaw was already absolute. Okay, this all sounds incredibly powerful, but for a practitioner deploying this in the real world, how do they know they can trust the math before they deploy it?
That is a crucial question. The paper is actually brutally honest regarding sample complexity.
So they don't just say, trust us, the Cascade works.
No, they offer a certified variant of the Cascade.
Yeah.
It gives an a priori distribution-free guarantee.
Okay, but there is a catch, right?
Yes. It comes with a strict data cost known as the rule of three.
The rule of three, break that down for me.
It is a statistical rule for estimating the maximum probability of an event you've never actually observed. In this case, accidentally failing a good run.
Okay, so based on the validation data they had, how does it play out?
Well, they had about 115 successful validation episodes. The math dictates that with that number, they can only certify a target up to about 97.4%.
So with 115 examples, they can prove they will save at least 97.4% of good runs.
Right.
But what if a practitioner demands a 98% or even a 99% safety guarantee?
The system literally abstains. It refuses to abort anything.
It just turns off the compute savings entirely.
Yes. Because it requires 1.3 to 2.6 times more data to mathematically prove that stricter promise.
Wow. So what does this all mean for you listening right now? It means you get a system that doesn't just save you compute, but transparently tells you exactly what promises your current data set can actually back up.
It prevents you from being overconfident. It is a fantastic safety valve.
It really is. Well, we've covered a lot of ground today. We've explored how looking inside an AI's residual stream at the very first round can predict failure.
Long before the surface text shows any errors.
And we saw how a mathematically calibrated cascade can safely pull the plug, saving massive amounts of compute without silently destroying good runs.
The efficiency gains are just undeniable.
They really are. But I want to leave you with a final thought to chew on, something beyond just the token savings.
Oh, this should be good.
If an AI's internal state knows it is doomed to fail long before it actually types a single incorrect word, it implies a certain level of latent awareness.
That is a fascinating way to look at it.
Right. What other complex human-like metacognition, things like doubt, certainty, or even deception, is hiding in that residual stream?
Just waiting for the right linear probe to uncover it.
Exactly. It really makes you wonder what else these models are thinking before they ever say a word. Thanks for joining us on this deep dive. See you next time.